Okay, so today we'll discuss and summarize the Laplace transform. So, Laplace transform are a set of mathematical operations which are useful to calculate the impulse response for a given LTI system. So, more specifically, we'll discuss one-sided Laplace transform. So, Laplace transform is defined as integral f of t to the power minus st dt, where s is sigma plus j omega. So this is similar to the Fourier transform, just that the mapping is from time domain to a domain which has exponential uh, uh, part of real plus imaginary times dt. So why do we need to introduce this concept? So firstly, they are used full in solving differential equations, and other some functions uh, uh, they do not have a well easy to compute Fourier transform. So we'll consider example of unit step. So the Fourier transform function would end up to be this term, which is not easy to compute since the behavior of e to power minus j omega t is not known at infinity. It is bounded between certain range, but the exact value is not known. So instead, if we take the Laplace transform, we get the similar type of relation, and now we have the value defined at infinity for a given choice of sigma, and hence the Laplace transform is given by 1 upon s. So Laplace transform for signals which are 0 for t less than 0 is same as the Fourier transform given s is equal to j omega. So here are some results. This one we have discussed. The Laplace transform of delta function uh, is similar to the Fourier calculations, and again the value comes out to be 1. Another important result is e to the power lambda t us of t. The Laplace transform is 1 by s minus lambda. This can be derived similar to this equation, substituting replacing 1 by e to the power lambda t and solving. So again there are properties which are similar to uh, Fourier transform. For example, uh, the linearity, the constant times the function is constant times the Laplace transform, and so on. Another important result is the Laplace transform of the derivative of function by partial laws of integration by parts. It can be written, it can be evaluated as f of s minus f of 0. So this is done by applying by parts, and since the for a given choice of sigma, the exponential term goes to 0. So we are left with only with minus f of 0 and plus s of s times the Laplace transform. So this is an important result, and this is similar to the Fourier result. Another important result is the Laplace of the convolution of two functions, or in this case the h of t and u of t is product of the Laplace transform of individual signals. Now this result can be used to calculate the impulse response and hence the overall general response for any LTI system. So first we will consider the first order LCC ODE to calculate the impulse response. As discussed, any LCC ODE is LTI, hence we can use the result that the output is convolution with the of the input with the impulse response. So now taking Laplace transform and using the relation of the derivative, we write this expression combining y of s and expressing it in terms of initial value, where y naught is y at 0 and the input. So this is the final expression in s domain. Now since on substituting u equal to 0, that is no input, we'll get a function, we'll get a value. So this represents the homogeneous part or the homogeneous solution, hence this must represent the particular solution. Now in time domain this can be expressed as y of t is homogeneous solution plus particular solution. This is because the particular solution when substituting ut equal to 0 shall give the homogeneous solution. So hence we are left with the term which has to be the particular solution. Now taking the Laplace transform of this and equating with the above equation, we'll get h of s equal to this term, since y of s equal to Laplace transform of this times the Laplace of the convolution, which is the products. So we'll get h of s equal to this, and through Laplace inverse, so we'll see this result. Basically take out t, so 1 by t, s plus 1 by t, and then use this result, we'll get the impulse response. So hence the Laplace transform is useful for getting impulse response, and we'll see in further videos that it is also used for getting step response, general response, etc. So again, quick summary that the given solution is homogeneous solution plus particular solution, and particular solution is convolution of the input with the impulse response. Okay, thank you.